Hello, it's me, Robert Jordan from Capful of Ghost Electronics, back with another Where is the EMS Spectre open source project at? You can probably see in the background we've got some fancy looking colours, and that is because, come on, there we go. So what we're seeing in the background here is a picture of some of the stuff that's done for the project so far. More has been done than you can see in that example there, but in terms of what is actually on a real world FPGA board, this is it. So I'm using a Digilant RTZ7. It's a pretty expensive FPGA because it's got a built-in dual-core ARM processor. I don't imagine this kind of thing would ever be on an actual product version of this, but it's just much easier to set up because I can just use the built-in processor stuff, sort of just like as is. I don't have to worry too much about building an internal processor inside the FPGA. Let's just run a few more little patterns. So what I'm doing at the moment is it's as though I'm randomly placing pins in the digital matrix. So I don't really know what's going to happen. Hey. It's pretty fun. All right, so what does that actually mean? So when you're working with projects that involve embedded processors like this one, whether you're in Quartus or Vivado in this case, you'll normally have a view like this, kind of blocky view, because you can do it just straight with code, but it gets a bit tricky and it gets hard to kind of, and a bit painful just to wire stuff together. What's nice about Vivado here is it's got some auto-completion stuff. It'll wire things together for you. So the matrix, all the different elements that come in and out of the matrix, like the X-timers and the flip-flops and all the kind of things that you wire together with the pin matrix, all of that is contained in this block. So that contains all the code I showed previously. And what I've added since then is this. So this is essentially generates the timing signals required to produce DVI video. Yes, it says HDMI, coming out of HDMI port, it's DVI. So it sends the horizontal and vertical syncs that I'm highlighting here, you can see, to the digital test side, and that's where all the stuff I've built so far lives, and it returns its video RGB, 8 bits for red, green and blue through to here, and then it passes them out as differential pairs to be the DVI standard. This Zinc is the ARM processor that's inside of the FPGA that we're using, and it needs a few things to keep it happy. It needs a reset generator. So ARM and Xilinx in general, who make this FPGA and Vivado, have gone down the path of the Axi bus. So you'll see a bunch of things with Axi on them. It's a memory mapped interface that lets the processor talk to things external to it as though they were just like a part of the memory range. And so in order to control the digital test side, a matrix, what I've done here is taken, this is just a normal BRAM controller, so a memory controller that you use if you had, say, external memory, external RAM. You could use it for internal memory, somewhere that you've got like a store of RAM that you can read and write to. I've written this here, which is like a interpretive layer that translates between memory locations and data that's treated as memory and writing to and reading from memory, and it turns it into the signals that our digital test side want, such as what address in the matrix, so input to the matrix, output to the matrix, latch, load, and this chip select. So anyway, once that's been written and it all looks happy, then we go to the synthesized stage. So that's where all the stuff that we've created here, the code that I've written, the block diagram, everything gets translated into, sorry, I'm going to have a drink. That's where all the stuff that we've written, all the stuff you saw in the block diagram, gets translated into the elements that are actually going to eventually go onto the FPGA. So it goes from code to a net list, to this interpretive layer that sits between the code that we've written and something that could actually go onto the FPGA. So if we zoom in, what can we see? We can see, I didn't talk about the buttons and LEDs, I've just got them there for test purposes. We can see that buttons we have coming in get buffered, they go into this EMS Spectre. So it doesn't look like there's much here. We can see all our outputs. Here's some debugging stuff that I've put in. We can see our memory, all the different kind of stuff that's set up there. Here's our DVI interface. So what it's done is it's rolled a lot of stuff. It's rolled a lot of our code into this big block here, Z Spectre I. So let's open that by itself. Boop. Come on. So in here, that's where we've got our BRAM controller, and if we really wanted, we could peep further into that and see what's happening in there. Because in this case, this is Xilinx IP, so we're not really going to see anything. Oh, yeah, not really. It's all still kind of obscured a fair bit. So what's cool about this is we can just jump kind of down as low as we want in the stack to see what's happened. So this is a part of debugging. Sometimes you'll find that the synthesizer doesn't do what you intended because you write code that the synthesizer then attempts to turn into logical blocks. And because of the way you've written it, because of the way the compiler, so the synthesizer works, you can be in positions of it just not doing exactly what you want. And so a good way to check without having to fully build the whole thing, put it on an FPGA, test it, is to be able to look at the signals here. So if one of these, was disconnected, if there was nothing connected to clock X, well then we'd know something had gone wrong in our code. But yeah, we can just jump straight in and see at a pretty minute level, we can see our X counter. Let's look inside our X counter. We can see LUTs, the lookup tables. This is a flip-flop and latch. That's a LUT with 6 inputs. At some point, I'll probably make a video talking about what these kind of different elements are and how FPGAs kind of go about making what you want logically turn into, anything. There's this idea that you can write anything and then it will be able to be synthesized if it can be synthesized. And so here is a little DIY board that I've made that combines 2 3-input LUTs and some other stuff together as kind of like a high-level way of showing how FPGAs work and how you can repeat, these same logical elements many times to achieve interesting things. So once we're all happy with that, we go to the implementation stage. So here's where those blocks you saw before, where the code we've written, which has now been turned into these synthesizable logic blocks, now gets turned into actual references to places within the FPGA. So what we're looking at here is actually the FPGA that I showed you before. kind of at a die level. And all these bluey green blocks, that's where stuff is. That's where the code that we've written has actually been placed within the FPGA. Lots of stuff here is empty. We can't see anything there. This thing over here is the hard processor. Along the edges, we've got the inputs and output ports. So let's go from the outside in. If I zoom over to here, here we go. So if we go right down to here, this is an actual pin output of the FPGA. In this case, it's called M14. We can click on Show Connectivity, and it will now show us where this pad is connected to. Of course, it's not traveling straight over the top here. It's going through a network of connectors and routers to get to the different places. But let's see, we'll zoom right in here. So these are called lots of things. Xilinx calls them slices, but you can see repeated here, we have a lot of the same things, these slices, and they're essentially, here we've got a bunch of LUTs, lookup tables, which can solve logical problems. They can do Boolean arithmetic, stuff like that. We've got some muxes here for combining those. What's this? This looks like a, oh yep, so this is a carry 4. So this is, this lets you turn these into a bit of an adder. And on the output, we've got flip-flops. So flip-flops let you store data in line with a clock or in line with another signal in order to use later. So we can see, as we look around, yeah, we've used a lot of stuff. Normally at this level, I don't really do that much debugging because there's not that much, to be done. What we can do is sort of see where things have been placed, where the elements that we're interested in have been put, because that's often a bit of a, that's we can see where stuff has been put, and that can often be quite useful. So here I've selected digital test side. That's my matrix, all the inputs and outputs, all the stuff that's been built so far, highlighted it yellow, and we can see here, kind of sitting through the middle here, that I don't see any problems there. That seems pretty consistent. If in the future we start running into some problems, maybe because we start running out of space, we can't fit all the things we want to into this chip. It's quite a large chip, so I don't think that'll be a problem. But we do have options of telling the implementer, telling the synthesizer, hey, this bit or this thing, I'd really want it close to the pin. I really want it close to the output, for whatever reason. I mostly just wanted to show this to be like, this is the actual code placed in physical locations upon the FPGA. And things kind of grouped together in these little spaces. Once that's all done, I'm using something called Vitus. So this is what Xilinx uses to let you write C code for their embedded processors. And so then within that, we have, ring-a-ding-ding, some pretty boring C code. It's probably a little small on this screen. Maybe I'll zoom in a minute. Yeah, and so what I'm doing at the moment is placing, we're going to jump back to the front webcam so you can see it. I've got a function here that just randomly inserts pins at random locations. And you can see, because we don't have all the features in there, and because of the way that, we just finished, and because of the way that we could be connecting something to something we're not looking at, something that never runs to the video output, when we do a random thing. So, don't go to that, computer present. But so at the moment, I'm using this to kind of test the matrix, make sure that the connections make sense, that I'm seeing what I think I should be seeing. I'll have an update in a little bit with how the shape generator is going. So the shape generator has got a fair bit going. It's in a kind of nice place at the moment. But yeah, I just wanted to do, I mean, I said quick, but I'm sure this has taken a bloody long time. I just wanted to show the actual code that's been written on an actual FPGA, actually running, actually making video that's actually being captured. Because I think it's very easy to get in your mind about, I think it's very easy to get in all up in your head about the code and imagining it in this kind of like nebulous software world. But it is actually hardware. It is actually real gates and LUTs, and it is real things connected together. It is real things on the FPGA. That what is very cool is that we can zoom into a minute level. Like we can grab this LUT here. Let's grab this LUT here. Like I can go right down to the level of looking at the truth table that it's implementing. What this does, no idea. How would I even tell? It's called B121401. Yeah, it's part of something. Okay, it's part of the pin matrix. It's part of the leaf cells of the pin matrix. Who knows? But if for whatever reason I needed to get down to this intense level, I can do that. So, thanks for watching. I'll probably edit this to be a bit snappier than the other ones, but such a pleasure. And I finished my plush mace. It's a big, beautiful, squishy plush mace for bopping. And now it lives on top of my computer. So stay tuned. I'm sure there'll be something very soon about more exciting things happening for the open source EMS Spectre. Till next time.